Welcome to a journey through the cosmos, where we explore one of the most profound questions humanity has asked. What is the fate of our universe? Is it destined to expand forever, tear itself apart, collapse back to a fiery singularity, or end in some sudden quantum catastrophe? Today, we'll delve deep into the current understanding, theories and scenarios that map the ultimate destiny of everything we know. Let's begin with the cosmic expansion itself. The universe is expanding, and crucially, that expansion is accelerating. This acceleration is quantified by the Hubble constant, often denoted as h0. But here's where modern astrophysics reveals a puzzle. Two key methods to measure this expansion rate produce conflicting results. The first method observes the cosmic microwave background radiation, the afterglow of the Big Bang, through satellites like Planck. These observations suggest an expansion rate of about 67, 4 kilometers per second per megaparsec. The second method uses what is called the cosmic distance ladder, key standard candles like type Ia supernovae and Cepheid variable stars, and finds a slightly higher rate, around 73 kilometers per second per megaparsec. This discrepancy, called the Hubble tension, is statistically significant and may point either to unknown systematic errors or new physics beyond our current models. Resolving this tension is a major aim for upcoming surveys and observatories. Driving this accelerated expansion is a mysterious entity called dark energy, making up roughly 70% of the universe's total energy density. Dark energy's behavior is described by its equation of state parameter, W, the ratio of pressure to energy density. If W is less than -1/3, the universe's expansion accelerates. The cosmological constant model, widely known as lambda CDM, assumes W is exactly 1, implying unchanging, constant acceleration. But alternative models exist. Quintessence treats dark energy as a dynamic field with W between 1 and 1 to 3, hinting at a future where acceleration slows. Current observations favor W extremely close to 1, showing no clear deviations yet. On the other end of the spectrum, phantom energy, where W is less than 1, implies ever-increasing acceleration, leading to a catastrophic Big Rip, tearing the cosmos apart at every scale. The fate of the cosmos thus hinges on measuring this parameter W with great precision. Even small departures from 1 could dramatically alter our universe's future. Now let's visualize the long-term futures given these possibilities. First, the Big Freeze, or heat death scenario. If dark energy is a cosmological constant, or behaves with W greater than or equal to 1 without diminishing, the universe will expand forever, cooling and darkening gradually. Star formation will cease in about 100 trillion years, as cold gas reservoirs deplete. Existing stars burn out, and galaxies slowly disintegrate into stellar remnants like white and neutron stars. Over unfathomably long timescales, around 10⁻40 to 10⁻100 years, black holes dominate, slowly evaporating via Hawking radiation. Once even these remain vanish, the universe enters a dark era, an extremely cold, sparse expanse of low-energy particles and near maximum entropy. This quiet, frozen state marks the ultimate heat death, where no meaningful work or activity can continue. In stark contrast is the Big Rip, predicted by phantom energy models. Here, the acceleration intensifies uncontrollably, eventually overwhelming all structures. Tens of millions of years before the end, galaxy clusters disintegrate. Galaxies dissolve months before. Solar systems fall apart mere minutes before the ultimate singularity, where space itself tears apart infinitesimally. At the Big Rip, physical laws as we know them break down entirely in a finite time. What about reversal? The Big Crunch is the mirror image of the Big Bang. If, under some scenarios, dark energy fades or turns attractive, the cosmic expansion could halt and reverse, collapsing all matter and space back into an extremely hot, dense state. This could end the universe in a final singularity, or intriguingly, trigger a bounce, a new Big Bang restarting the cosmic cycle. Such oscillating or cyclic models remain speculative without observational support, but offer a fascinating alternative. Beyond gravity and expansion, particle physics introduces another cosmic threat: vacuum decay. The quantum fields that determine our universe's properties might be in a metastable state, susceptible to tunneling into a lower energy true vacuum. If this occurs, a bubble of true vacuum would expand at light speed, rewriting physics inside and obliterating all structures. Fortunately, current estimates suggest such an event, if possible at all, has an average lifetime trillions upon trillions of times the universe's current age, so it's not an imminent concern. Underlying many endings are subtle but inevitable processes: proton decay, neutron decay, and black hole evaporation. The proton, once assumed stable, may decay over periods up to 1036 years, slowly dissolving all baryonic matter. Neutron decay is more immediate for free neutrons, but irrelevant in stable nuclei until proton decay destabilizes atoms. Black holes, too, wane very slowly through quantum emissions over time periods much longer than current cosmic age. Combined, these ensure ordered structures eventually fade, driving the universe toward maximum entropy and equilibrium. Speaking of entropy, the universe's thermodynamic journey is toward heat death. No usable energy gradients remain, and all processes cease. This fate constrains life and consciousness, including advanced civilizations' ability to compute or process information. As temperatures drop, energy costs for erasing information decline but cannot vanish entirely, setting fundamental limits on potential future activity. An intriguing theoretical issue arises from Boltzmann brains, hypothetical self-aware entities arising by random chance in an eternal, high-entropy universe. Their possible prevalence challenges our understanding of typical observers and suggests either the universe won't last forever, or that our assumptions about probabilities need refinement. To assess our place in cosmic time, anthropic and probabilistic reasoning offers perspectives like the doomsday argument. This controversial line of thought uses our temporal birth rank to infer limits on humanity's future. Whether or not one accepts such reasoning, it reminds us of observer selection effects. The fact we exist inherently biases the observations we can make about the cosmos and its parameters. Looking forward, astrobiology indicates that while the current era is fertile for life, over trillions of years, fewer stars remain to host habitable worlds. Advanced civilizations, if they survive, might engineer solutions: Dyson spheres to capture every watt of stellar energy, star lifting to prolong stellar lives, lighting dead stars anew, or harnessing black hole energy via complex processes. Yet even these feats confront ultimate thermodynamic and cosmic expansion constraints. The next decade promises breakthroughs to refine our knowledge and perhaps answer some of these mysteries. Missions like Euclid and the Nancy Grace Roman Space Telescope will map billions of galaxies and distant supernovae to nail down dark energy's nature and cosmic expansion history. The CMB Stage 4 project will provide unprecedented views of the early universe's imprint, probing neutrino physics and testing new physics hypotheses. Gravitational wave astronomy opens a novel window using standard sirens from neutron star mergers to measure distances and expansion independently. On the particle physics front, upgraded colliders and neutrino observatories aim to measure the Higgs boson and top quark properties vital to understanding vacuum stability and search for signs of proton decay, potentially validating grand unified theories. However, many fundamental questions remain open. Is dark energy truly constant or dynamic? Will our vacuum remain stable or suddenly decay? Does unification imply proton decay? What is the nature of dark matter? Does quantum gravity resolve singularities and allow cosmic bounces? How will life and intelligence endure? Answering these requires a multidisciplinary global effort, combining cosmology, astrophysics, particle physics, quantum gravity, and even philosophy to grapple with measure problems and observer selection. To conclude, here is a rough cosmic timeline, mapping possible future milestones. In around 10 or 14 years, star formation will cease, marking the end of the stelliferous era. By 10 to 15 to 10 plus 16 years, the last red dwarf stars will burn out, leaving stellar remnants. Galactic structures disperse over 10 or 19 to 10 or 20 years as gravitational encounters eject stars. If proton decay occurs, it unfolds over 10 or 34 years, eventually dissolving atomic matter by 10 or 37 years. The black hole era spans roughly 10 or 40 to 10 or 100 years, while black holes evaporate, ushering in the dark era with near absolute zero temperatures. If phantom energy dominates, the Big Rip may occur within 10 to 100 billion years, tearing apart everything in a violent end. The Big Crunch, if possible, would happen even later, after a hypothetical cosmic contraction phase. Vacuum decay could strike any time, though likely over unimaginably long timescales around 10 or 139 years. Our universe's fate is vast in time and scope, filled with intricate physical phenomena and profound mysteries, blending the cosmological with the quantum. With persistent observations, experimental advancement, and theoretical insight, humanity edges closer to uncovering which path our cosmic home will follow: a serene, eternal expansion, a catastrophic rip, a cyclical rebirth, or a silent quantum transformation. Thank you for joining this voyage through cosmic destiny. Stay curious, for the universe always has more to teach us. We hope this exploration has enriched your understanding of these profound scientific concepts. For more in-depth analysis of complex phenomena, consider subscribing to our channel. Until our next examination of the ever-evolving world.